On the 4th of November 2025 at 5:13 p.m., a UPS MD-11 freighter lifted off runway 17R in Louisville carrying 3 crew members, 20,000 packages, and 38,000 gallons of fuel for Hawaii. The NTSB preliminary report states the plane reached an altitude of just 30 feet, clearing a runway fence, before coming down. I've spent hours analyzing the flight data, the ADS-B tracks, the surveillance footage. Here's what doesn't make sense. This wasn't a stall, wasn't a bird strike, wasn't weather. The left engine, with the bulk of its pylon still attached, separated from the wing and flipped backwards over the wing's leading edge shortly after rotation. 30 feet, that's the height of a 3-story building. Understanding why this crew never had a chance might prevent the next catastrophe. UPS Airlines Flight 2976 was a scheduled domestic cargo flight from Louisville Muhammad Ali International Airport to Honolulu, Hawaii, departing at about 5:13 p.m. local time on the 4th of November 2025. Weather at the time was clear, with wind at 6 knots from the southeast with visibility of 10 miles. Nothing suggested the nightmare that was about to unfold. The aircraft, N259UP, was a 34-year-old McDonnell Douglas MD-11F, first delivered to Thai Airways International in 1991, later converted to a cargo aircraft, and delivered to UPS Airlines in 2006. It had flown 21,043 cycles and for about 92,992 hours, and was equipped with 3 General Electric CF680C2D1F turbofan engines. For context, 1 cycle equals 1 pressurization, essentially 1 flight. This airframe had accumulated decades of takeoffs and landings, each one stressing the metal structures that held its massive engines to the wings. The 3 crew members were Captain Richard Wartenberg, First Officer Lee Truitt, and International Relief Officer Captain Dana Diamond, all pilots. They were experienced MD-11 operators preparing for the long Trans-Pacific crossing to Honolulu, an 8.5-hour flight over open ocean. The plane was carrying up to 20,000 packages and 38,000 gallons of fuel. This was a maximum weight departure, the aircraft loaded to its operational limits. Louisville Muhammad Ali International Airport is home to UPS Worldport, the company's massive sorting hub. Hundreds of flights operate through this facility daily, making it one of the busiest cargo airports in North America. Flight 2976 was routine in every way, until it wasn't. The plane received takeoff clearance at about 17.11 EST. Standard procedures for an MD-11 departure: taxi to the runway, run through final checklists, align with the center line, advance the throttles on all 3 engines. The taxi and takeoff roll went as routine. The airplane rotated for takeoff at approximately 17.14 EST. For a heavily loaded MD-11, rotation speed, the speed at which pilots pull back on the controls to lift the nose, would be around 165 knots. The aircraft accelerated down runway 17R, its 3 engines producing combined thrust of over 180,000 pounds. V1, the go, no-go decision speed, would have been called around 150 knots. Past that point, the crew is committed, there's not enough runway remaining to abort safely. But something catastrophic was already happening. During takeoff, shortly after rotation, the left engine, with the bulk of its pylons still attached, separated from the wing and flipped backwards over the wing's leading edge. As it detached, a fire ignited on the engine, and it tumbled up and over the aircraft, coming to rest on the grass on the right side of runway 17R. Surveillance footage from the airport captured the horrifying sequence. The engine, weighing over 10,000 pounds, tore free at the moment the aircraft's nose lifted. In the cockpit, alarms would have erupted. Fire warnings, engine failure indications, hydraulic cautions. But there was no time to process what was happening. The MD-11's wheels left the pavement, and the crew was airborne with a structurally compromised aircraft. It started its climb but did not get higher than about 30 feet above ground level. Let me put that in perspective. When an engine separates from a commercial aircraft, it's not just losing thrust. The sudden asymmetry creates massive aerodynamic forces. The aircraft wants to roll toward the dead engine. It wants to yaw, turn sideways into the void where an engine used to be. Pilots train for engine failures. But those scenarios assume the engine fails but remains attached. This was fundamentally different. A fire also broke out near the left pylon attachment point and continued to burn until impact. The pylon itself, the structural beam connecting the engine to the wing, had fractured. Without that structural support, the wing's aerodynamics were compromised. The smooth airflow over and under the wing that generates lift was disrupted by the torn metal, the trailing fire, the exposed mechanisms. A witness in the control tower reported that the plane had normal takeoff speed, but the climb was not. Another witness added about how the plane stopped climbing and started to lose altitude before rolling to the left. The aircraft barely cleared the blast fence at the end of the runway. In my experience analyzing accidents, when a fully loaded aircraft can't climb past 30 feet with 2 functioning engines, something has fundamentally destroyed its ability to generate lift or control its trajectory. The jet's left main landing gear struck the roof of a UPS supply chain warehouse, leaving a 300-foot gash. The last ADS-B message, received at 5 hours 13 minutes and 32 seconds p.m. EST, showed the aircraft had reached a maximum speed of 183 knots and an altitude of 475 feet above sea level, only 10 feet above ground level. Weight 10 feet above ground level at that position means the aircraft had descended below the airfield elevation after initially climbing to 30 feet. It wasn't maintaining altitude, it was falling. An NTSB spokesman said the CVR audio contained a persistent bell sound. That bell likely represented multiple warning systems activating simultaneously: fire warnings, configuration warnings, possibly stick shaker alerts indicating an approaching stall. The crew had seconds to comprehend an impossible situation. The MD-11 rolled left and descended into an industrial complex south of the airport. The crash killed 15 people, which consisted of all 3 crew members on board the aircraft and an additional 12 people on the ground, one of whom succumbed to their injuries on December 25. The debris field extended over half a mile. The fuel ignited on impact, creating a fireball that witnesses described as apocalyptic. From engine separation to impact, approximately 20 seconds. The data tells us what happened. The question is why? The leading theory emerged within days of the accident: catastrophic failure of the engine pylon mounting structure. The NTSB preliminary report stated that inspection of the pylon showed fatigue, cracks on both fracture surfaces of the aft mount's aft lug and along the bore of the aft mount forward lug's inboard fracture surface. Metal fatigue is insidious. Each flight cycle, every pressurization and depressurization, every takeoff and landing stresses the aircraft's structure. Microscopic cracks form at stress concentration points. Over thousands of cycles, those cracks propagate through the metal. Eventually, the component fails catastrophically. The pylon aft mount is subjected to enormous loads. The engine's weight hangs from it during flight. The engine's thrust pushes through it during takeoff. Vibrations from the spinning turbine transmit through it continuously. This isn't a component that fails gradually with visible warning signs. When it goes completely. Similar failure modes have occurred before. The most infamous parallel is American Airlines Flight 191 inches, 1979, a DC-10 that lost its left engine and pylon on takeoff from Chicago O'Hare. That accident killed 273 people. The MD-11 shares structural lineage with the DC-10. The mounting system is fundamentally similar. Investigators immediately recognized the parallels. Theory 2. The inspection intervals were inadequate for detecting progressive cracking in this component. The last visual inspections of the left pylon aft mount were performed in October 2021, more rigorous. Special detailed inspections for the mount lugs and wing clevis were not yet due, as the aircraft's 21,043 accumulated cycles were well below the 28,000 and 29,200 cycle thresholds required for those checks. Think about that timeline. The last detailed inspection was in October 2021, over 4 years before the accident. In that time, N259 UP completed thousands of flight cycles. Lubrication of the pylon thrust links and spherical bearings was performed on the 18th of October 2025, 17 days before the accident. Maintenance personnel lubricated the bearings just weeks before the crash. Could they have missed visible evidence of the bearing race migrating from its proper position? The challenge with fatigue cracks is that they often aren't visible until they've propagated through most of the component's thickness. A surface inspection might reveal nothing even when the internal structure is severely compromised. The question for investigators: should these components have been inspected more frequently, or replaced proactively based on cycle counts regardless of visible condition? Theory 3 is the most troubling. Boeing knew this specific failure mode was possible and didn't mandate corrective action. According to the NTSB's January 2026 investigative update, Boeing Service Letter MD-11SL54104A, dated February 7, 2011, informed operators of 4 previously reported bearing race failures on 3 different airplanes involving this exact part. Let that information settle. 4 documented failures of this bearing. Boeing issued a service letter recommending inspections and offering a redesigned bearing that eliminated the problematic design recess groove, but crucially, they concluded the failure would not result in a safety of flight condition. Installation of the improved part was voluntary, not mandatory. Some analysts believe this assessment was catastrophically wrong. A former FAA investigator noted that a 1980 McDonnell Douglas service bulletin identified spherical bearing race failures as a safety of flight condition. Why did Boeing downgrade that assessment in 2011? What analysis led them to conclude that an engine pylon mount failure wasn't critical enough to mandate retrofits? This is where accident investigations become uncomfortable. They reveal not just mechanical failures but institutional failures, decisions made years earlier that, in hindsight, appear inadequate. When I examine all the evidence together, the failure progression becomes clear. A design flaw in the bearing race created a stress concentration point where fatigue cracks could initiate. Over N259 UP's 21,043 cycles, those cracks grew incrementally. The inspection intervals couldn't detect the progressive damage. During the high loads of takeoff rotation on November 4th, the aircraft at maximum weight, the engines at maximum thrust, aerodynamic forces at their peak, the bearing race fractured completely. The engine and pylon assembly separated. Without that structural attachment, the engine couldn't be controlled. It tumbled over the wing. Fire erupted immediately as fuel lines ruptured. The aerodynamic disruption to the left wing was catastrophic. The aircraft rolled left, unable to generate sufficient lift or maintain directional control. The NTSB investigation will likely focus on three key questions. Why did Boeing assess this failure mode as non-critical in 2011? Should the FAA have mandated the improved bearing as an airworthiness directive? Were UPS's maintenance intervals adequate given the known failure history? But there's something else that's been bothering me about those final 30 feet. Put yourself in that cockpit. You've just rotated for takeoff. The nose is lifting. Suddenly, catastrophic failure indications illuminate across your instruments. Fire warnings. The aircraft shudders violently. You hear, perhaps even feel, something massive separate from the airframe. Your training says, fly the aircraft first, diagnose second. But what can you fly? Standard engine-out procedures assume you have two functioning engines and intact flight controls. The aircraft subsequently entered a descent. The crew would have applied full right rudder to counteract the left yaw. They would have pushed the control column forward to maintain airspeed and prevent a stall. They would have advanced the remaining engines to maximum thrust. None of it mattered. The aircraft was structurally compromised in a way no simulator prepares you for. When investigators analyze crew resource management in this accident, they'll find professionals executing procedures perfectly in a situation where no procedures could help. The workload was overwhelming. The time available was insufficient. The aircraft's ability to respond to control inputs was fatally degraded. This wasn't crew error. This was an impossible situation created by a mechanical failure. N259 UP had a complicated history. The plane had been in San Antonio for about 6 weeks before Tuesday's flight, and officials said they are looking into maintenance records from its time in Texas. The MD-11 itself represents a dying breed, a trijet design from an era when twin-engine aircraft weren't yet reliable enough for long over-water flights. Airlines abandoned MD-11 seconds for passenger service years ago due to fuel inefficiency, but cargo operators like UPS and FedEx continued flying them. The accident forced a global reckoning. UPS voluntarily grounded its entire MD-11 fleet immediately. The FAA issued an emergency airworthiness directive, prohibiting MD-11 operations pending inspections. That directive later expanded to include DC-10 aircraft with similar pylon designs. The grounding disrupted cargo operations across multiple continents, but the alternative, continuing to operate aircraft with potentially compromised engine mounts, was unacceptable. The parallels to American Airlines Flight 191 are chilling. Both accidents involved left engine separation on takeoff. Both aircraft were part of the DC-10 MD-11 family. Both resulted in immediate loss of control and catastrophic crashes. The 1979 accident led to design changes and improved inspection protocols. Apparently, those changes weren't sufficient. Beyond the technical failure lies uncomfortable systemic questions. How did a component with 4 documented failures remain in service with voluntary inspection recommendations rather than mandatory replacement requirements? The answer involves the complex relationship between manufacturers, operators, and regulators. Service letters are recommendations. Airworthiness directives are mandates. When Boeing issued that 2011 service letter, they were alerting operators to a known issue and suggesting solutions. But they classified it as not creating a safety of flight condition. Without that classification, the FAA had no basis to mandate corrective action. UPS followed the prescribed maintenance program. They inspected and lubricated components per the schedule. The special detailed inspections that might have revealed the crack propagation weren't yet due based on cycle counts. From a regulatory compliance perspective, everything was in order. The accident reveals a gap in the safety system. When a manufacturer identifies repeated failures of a critical component but doesn't classify it as safety critical, how does the regulatory process ensure adequate protection? This is the kind of systemic question that often leads to significant regulatory changes post-accident. Every accident is a chain of events. Break one link, mandate the improved bearing in 2011, or establish more frequent inspections and 15 people would still be alive. For pilots operating older aircraft types, this accident reinforces several critical lessons. First, understand your aircraft's known vulnerabilities. The MD-11's engine mount design had documented failure modes. Situational awareness includes knowing what can break and what the consequences might be. Second, recognize that some mechanical failures create unrecoverable situations. Training and skill matter immensely, but structural failures during critical phases of flight may simply exceed the aircraft's ability to compensate. This isn't defeatism, it's acknowledging reality. The best prevention is ensuring the aircraft doesn't break in the first place. Third, advocate for proactive maintenance philosophies. When manufacturers issue service letters about components with failure histories, operators should seriously consider whether voluntary is sufficient or whether mandating replacements would provide appropriate safety margins. Finally, understand that the decision to continue or abort a takeoff past V1 is predicated on assumptions about the aircraft's structural integrity. If you have indications of structural failure, unusual vibrations, visual evidence of parts departing, that calculation changes fundamentally. Sometimes, the runway remaining behind you is preferable to the sky ahead. The crew of Flight 2976 executed their duties professionally in an impossible situation. The failure wasn't theirs. The crash killed 15 people, all 3 crew members on board and 12 additional people on the ground, one of whom succumbed to injuries on December 25. Gov. Andy Bashir said that a young child is believed to be among the dead. Captain Wartenberg, First Officer Truitt, and Captain Diamond were experienced aviators executing a routine cargo flight. The ground victims were workers at industrial facilities, people who had no reason to expect their Monday evening would end in tragedy. According to Louisville's Mayor Craig Greenberg, the aftermath was unlike anything the city has seen in decades. Families waiting in Honolulu for cargo that would never arrive, colleagues at UPS Worldport grieving their lost crew members, an entire community traumatized by a disaster that unfolded in their neighborhoods. We owe these 15 people more than investigation reports and regulatory updates. We owe them prevention. The NTSB's final report will take up to 2 years to complete. When it arrives, it will likely contain safety recommendations addressing inspection intervals, mandatory component replacements for aging aircraft, and enhanced oversight of known failure modes. This channel will provide updates as the investigation progresses and final findings emerge. The fragility of flight, the fact that so much depends on small metal components performing flawlessly under enormous stress, demands our constant vigilance and our commitment to learn from every failure.